Running everybody, we continue talking about some difference in statements that can influence on model behavior and on a result. And today we talk shortly about mesh. This is default mesh and result for default mesh. Mesh without any preferences contain about 18,000 of nodes and around 10,000 of elements. It have a result like 567 microns of deformation and 243 megapascals. On the statement we see three faces that are fully fixed. Here we see force 10,000 of newtons, and we can see bonded connections for all parts. Also we can see that our object have the same material, structural steel S275N, and those material are linear. So we change mesh and what we obtain. With default mesh we have around 2 elements here, around 2 elements here on this neck, and 1 or 2 elements on this side of this neck. Also we can see that in this face we see mesh with less size than on this. Okay, let's change default mesh for 20 millimeters. We obtain 14,000 of nodes, 7,500 of elements. We see 1 element here, 1 element here, almost 2 elements here, and bigger elements here than with default mesh, but we see that these mesh are not so big as here. Okay, let's check all other mesh. This is 15 millimeters, and we see almost the same picture for this mesh as in default settings. The difference is here we see 1 element on this side, not 2. Also we see that number of nodes and elements are almost the same as on default mesh. It's almost 18,000 of nodes and 9,000 of elements. Okay, let's change mesh again. 10 millimeters. We have 2 elements here, we have 2 elements here, we have 4 elements here, we have almost uniform mesh size on this part, we have almost uniform mesh on this part, but it's not the same with this. We also see 29,000 of nodes and 15,000 of elements. With 5 millimeters we see almost uniform mesh in all cases, in all places. We have 60,000 with half of nodes and almost 31,000 of elements. And the last mesh is 2 millimeters. We have a lot of elements here. It's very important we have a lot of elements here. And we have 177 with half thousand of nodes and 93 with half thousand of elements. So changing size of mesh, increase number of nodes and elements, do better description of geometry, the better distribution and more uniform mesh for different cases, and for this case, not for all cases, a number of nodes are linear, have linear linear law of changing depending on mesh size. So if we change mesh size 10 times, we obtain almost 10 times bigger number of nodes and elements. Okay, now let's take a look into some picture of deformation and stress distribution. For deformation, we see 567 microns. We see picture. We see the same picture for all other results. For all other results, we see the same picture, but we see changing of this maximum value. With coarse mesh, we have 548 microns. With base mesh from the list, we have 595 microns. So it's around 10% we have change of this value. But picture of deformation, behavior of deformation, behavior of translation and deformation distribution are the same for all tasks, for all different type of mesh. It seems that in a behavior for deformation, even this coarse mesh are not very bad, and this one too. Default mesh are good, and we have 10% of difference, so around 10% of error for default mesh for those cases. Not for all times, not for all tasks, but for this. Because we have geometry which have size limits which are very close to size of all objects. So we doesn't have very wide, very long object and so on. We have not very small thickness for object and so on. So that's why we have only 10% of difference between those calculation and those calculation. And it's a 10% of difference for linear task with linear material behavior and with linear contact, bonded contact. Okay, it's very important things, and let's take a look into our stress distribution. We see that maximum here. We see some points here. We see 236 megapascals of maximum stresses. We see some place with higher stress, but in most cases it's very low stresses on all other places except this one. Also, we see stress distribution which look like here. If we take a look to stress distribution with default mesh, we see the same stress distribution. We see the same place of maximum. We see the same level of stresses. it has less than 5% of difference, but default mesh have not very big difference in mesh size with coarser mesh. Okay, if we take a look into 15, we'll see the same picture. If we take a look to 10, we see some difference. We have higher stress, higher maximum stress. It's almost 400 megapascals. It's 386 megapascal. This is 236. This is 386. So if we take calculator, 386 minus 236, it's almost 150 megapascals. And if we divide it to 236, we have 63% of difference in maximum value of stress. It's a very big difference. It's not bad, because we need to explain why it's so big, but we can't use this number for comparison those calculation. Also, we see that we have some difference in behavior. We see that here we doesn't see any light blue line, and on 10 millimeters we have something which can be this light blue color. Also, we see this line on a smaller mesh and on minimum mesh. But take a look, we see this type of color distribution with changing the original scale in ANSYS. If you take a look, we have from 0 to 200 degrees couple number of colors, and all that higher than 200 it's red, and that's the same scale to all our pictures. And we see analogical stress distribution. If we reset those scale and reset those scale, we'll see very big difference in stress distribution. Here we see red example, we see yellow and green here, and here we see light blue here, and no place with red. It's reason because we have a point with hotspot, and this point with hotspot have infinite stress in theory of elasticity. So in linear behavior we have here some places, some points where stresses must be infinite. In reason that we solve it not analytically but numerically with finite element mesh, we can't obtain infinite results, but we will obtain big range of stress, and it will be much bigger if we do smaller mesh. So, if you want to comparison stress distribution for different type of meshes with different mesh size, you must do it with the same scale. For example, as we do here. And if we take a look on this and on this picture, we see almost the same. Yep, we will see some differences. We see, for example, this line. We see some differences in those places of distribution. We see new place with maximum stresses. For example, this one. And we can see it here. We can see that this is concentrator. We can see that in those places we have stress that look like this one. So this is place of hotspot, but we doesn't see higher stress here because of mesh size. Because this stress distributed on all elements, on big elements. And here we have distribution of stress on small stresses, on small elements. So, if we take something like this area and average stress that we have here, we obtain the same picture as we have here. So, that is a problem of coarse mesh. In coarse mesh, we average all stresses with very big elements. So sometimes we can not obtain a place of hotspots, not obtain the real places with problem. So you need change your mesh to obtain good stress distribution. If you want to analyze stress, you need to obtain good stress distribution in those objects that you need. If you need this one, you not interested in those hotspot stresses. If you want to analyze all places near the scrunk, you need to do better mesh for obtaining something like that here in stress distribution. You don't need to improve wall mesh for all your parts with uniform size. It can be done with different methods, but you need to improve your mesh in some places. Okay, and also you need to understand that sometimes with changing size of elements from bigger to smaller, you can obtain, even in place with hotspots, stresses that will be not higher but lower than with more coarse mesh. With 10 millimeters we have almost 400, 386 megapascals here, and with 5 millimeters we have 320 megapascals here. It depends on many reasons. It depends on bonded contact between those two parts. It depends on position of elements and nodes. It depends on many different type of tasks. And also you might understand that this construction have several places with hotspot stresses, with local stresses that would be very big or infinite. It's a those corner near fixation. It's a those place, and it's for base and for cronk. It's for those place here and for those place here. And symmetrically you have the same picture on this side. So this place and this place will have limited stress range because you doesn't have here a sharp corner. On this place you have sharp corners, and in this reason you will have on this place and on this place for base and for cronk very high stresses. For this one, for base, unlimited. For this one, unlimited in those points if you use contact. So when you change size of your mesh, this stress will up sometimes, will stay bigger, and they became to the adequate physical range and will stay on the same digit, on the same value. At this place, on the corner of fixation, at this place, you will have theoretically infinite stress. So in those places, with changing the size of elements, number it's 1 divided by size of elements. So number depends on size elements, and when we decrease size of elements, we increase number of elements. And stresses will go to infinite. But it will not go by this way. It will go something like this way. So sometimes with smaller mesh we can obtain less value than with coarser mesh on some hotspot stresses. But in general, the law of stress distribution will be like this one. And for places with rounds without infinite stresses, it will look something like this one. So it became to some value, it can jump, but it will stay after some size of elements. And when you need to understand do your mesh are correct, do your mesh is adequate, has adequate size, and so on, you need to check your stress distribution or total deformation distribution or distribution of that result that you want to use as a result in your design. You can check distribution of results not only with equivalent but with directional, with normal, principal, and so on, depending on those results that you try to use. If picture, if stress distribution are not changed, that's a good mark for you. You must check result not in hotspot stress, but in some place which are near this hotspot, but not on hotspot. So, not in this place, but for example, here, here, here. For example, you can use here because you doesn't obtain infinite results here. And you draw this picture, how it change. You also can draw this picture, how change your stress in local hotspot with infinite distribution. But for your task, much more important, the blue one. And you must check your mesh with two different mesh size. The base mesh, which you will use on your finite element analysis, and size of this base mesh, size of elements, divided by 2. If stress distribution, if deformation distribution, temperature distribution, and so on are not changed, and if in object which are not hotspots, you will have error less than you need. It's around 5 to 10% in most engineering calculation of difference. You can use those mesh even if you have much more difference in hotspots. It's a very general approach, so in some different tasks it can be changed, but it's something like that to analyze how your mesh size influence and affect your calculation and your finite element results. Hope it will be helpful for you. Write a question if you have it. Bye.